Hello physics students, welcome back. Last time we talked, we learned about electric charges. Today we're going to learn how to calculate those electric charges. And what do I mean by that? I can show you this again. So you guys learned about tribal electric charging in the last video. If I take this glass rod and I charge it up, as you can see, it will pick up little bit of pieces of paper. You can kind of see that like this. It's kind of have an effect on them, okay? But in this section, we are going to learn how to actually calculate that force between there and there. So how do we calculate that force? It's really not too hard. Pretty easy calculation. We need to know a few things. Well, first of all, we need to know the charges on, let's call the glass rod Q1, let's call the paper Q2, so we would have to know the charges on those. And then the other thing we'd have to know is the distance between the glass rod and the piece of paper. And basically that's it. Kind of a fun fact here is if you double the charge on one of them, it's going to double the force. So if you double Q1, so if I charge that thing up even more, which I could do that, just give it a few more charges, it'll actually pick up the paper. If I charge up even more, it's going to double the force. Or vice versa, if I charge up the piece of paper. So I added more charge to it, as you can see. Oh, almost did it. If I go carefully here, I'm going to try a smaller one. Almost. It almost picks up the whole piece of paper. So yeah, if you double the charge, it's going to double the force. If you double the distance, it's actually going to quadruple it by a factor of 4, I should say. So here's our formula to calculate the force. It's like I said, it's pretty easy. So if we want to know the force between the glass rod and the piece of paper, we just need to know the magnitude of Q1, so the glass rod, the magnitude of Q2, the paper, and then the distance between the glass rod and the paper, which would be R squared. Q will be measured in coulombs, R is going to be measured in meters, so the distance is measured in meters. Because that goes along with our coefficient K, which is 8.99 times 10 to the 9th power, and it's Newton times meters squared divided by the coulombs squared. That's so these units cancel out with these units, and we're left with just the Newton. So the force, the SI unit for the electrostatic force, will be in a Newton. So let's kind of look at this for a nice picture of what's happening. The other thing to consider with electric forces is the charge, whether it's positive or negative. You guys know that opposites attract and that like charges will repel. And it can be drawn in a straight line right here. As you can see that if we have a positive charge Q1 and a positive charge Q2, well, that force can be drawn in the opposite direction because, well, you guys know that same charges repel. So this force will be here, and this force could be here. We draw the force with this little notation. So we have Q1, Q2. So the force on charge 1 by Q2 can be drawn right here. And the force on Q2 by 1 will be right here. So here is showing it that the opposites attract. You guys know those forces are going to be pulled toward each other. So again, you have force of 1 by 2. This would be the force of 2 by 1. It's very important to understand this when we start talking about the magnitude and the sign. It's kind of nice to know where these charges are going to be going. I'll show you some problems, so just keep this idea in the back of your mind. So when we calculate the electrostatic force, the direction will come into play when we're starting to talk about is it negative, is it positive? And I'll show you some examples of that in the next couple slides. So let's see here. Let's find the electric force between 1 coulomb charges separated by 1 meter. We are going to use the absolute value bars for Q1 and Q2 because we could have a negative for the electric charge. So we don't want to deal with a negative number, so we just say absolute value and absolute value. So to calculate, it's pretty simple. You just take 8.99 times 10 to the 9th power, and you multiply that over here by 1 times 1, there's the charges, divided by 1, and we get 8.99 times 10 to the 9th power. I did enter this into my calculator, which, yeah, it's over here. I did enter Coulomb's law into my calculator, and I'll show you guys. Hopefully it shows up on the phone here, and then you can hit pause on the video. So let me go like this, because we will use this quite a bit. But if you want to program this into your TI 83s, let me actually grab my phone so you guys can see what I did. Alright, zoom in on that now. I gotta tap the screen. There we go. So if you guys want to hit pause, that's what I did for my calculator. I couldn't do a Q1 and a Q2, so in the program I put Q, G, and then R. And then I stored it to F, so it displayed F. So if you guys want to hit pause on this video, I recommend plugging this into your calculator, so then all you have to do is enter in those three, the Q, the G, and the R, and it'll have your calculation for you right now. But there it is. Okay. And the other thing I recommend doing is storing K, that constant, into your calculator as well. It'll be kind of handy a little bit later on. So yeah, I have this in my calculator. So for instance, I just have to put in 1 here, 1 here, and 1 in there, and boom, it calculates it for me. So it saves you a lot of time. All right, let's look at another problem here. So 13, at what separation distance is the electrostatic force between a 11.2 microcoulomb point charge and a 29.1 microcoulomb point charge equal in magnitude to 1.77? So if we draw this out, it'll help us understand what it's asking us. So here's what we have. We have a point charge, positive, that has a charge of 11.2. We have another point charge over here that has a charge of 29.1, and it's positive and positive. And then there's the question's asking us, what is the separation distance? So it wants us to find this, okay? The force acting on the two is given, and if I draw this in, let's call this Q2, and let's call this point Q1. This would be the force of 2, or of, 2 by 1. That force is going to be equal to 1.77 newtons. There'd be another force over here, equal in magnitude as well. So there's kind of the picture of what it's asking us to find here. We're trying to find the distance between those two charges. So we can use our formula here. So force equals, it's that K, and then it's Q1 times Q2 all over R squared. We can plug in the force. We know the force is 1.77 equals K. I'm going to leave that constant. I got that in my calculator. I don't want to write it out every single time. We know the point charges are going to be 11.2 times 29.1 respectively there, all divided by R squared. So now we're just going to solve that for R. So multiply each side by R squared, just doing our algebra. Multiply this side by R squared. And then you're going to divide. So R squared equals K times 11.2 times 29.1 when I'm simplifying it. And then we'll divide by 1.77. So then that'll cancel out. And we're close. We'll have to take the square root of it to get our R. So to figure out the distance between the two, we'd have to plug that into our calculator. When you do that, we're going to get an answer of 1.29 meters. So the distance between those two charges would be 1.29 meters. So just doing a quick summary, we were given 2-point charges. They had a positive charge each, so this is the drawing of it. They're each going to have a force. It's going to be a repelling force. And we wanted to figure out the distance that separates them. So we used Coulomb's law, this formula, to figure that out. We knew the force, we know K, we knew the Q1 and Q2, so we just had to rearrange this for R, and we got 1.29 meters. So the distance between them, 1.29.
Have your attention, please. Teachers will be here for the members of the local 1691 union at about 12:15 in the guidance office. Thank you.
All right. So then let's look at another one of these. It says the repulsive electric force between the point charges, and then we have a negative value there, and Q has a magnitude of 1.32 newtons when the separation between the charges is 1.07 meters. Find the sign and magnitude of the charge Q. Okay, so we're going to use Coulomb's law again. So force equals K times Q1 Q2 all over R squared. I like to draw on the picture because it really helps. Well, because this problem asks us for the sign and magnitude of the charge Q. So the picture is going to help us kind of figure out, well, what do you mean by the sign? Well, the sign is positive or negative, okay? But when we draw on the picture, we have Q1, Q2. We know that let's call this one Q1. We know Q1 is a negative charge, so this is going to be a negative charge, okay? And we know the magnitude on that is going to be negative 6.36 times 10 to the negative 6 coulombs. Okay, if you read through the problem, it says the repulsive electric force between those 2-point charges. All right, so it's not an attractive force, so that's a big clue to the charge on this Q2 over here. Because it's repulsive, we know that it's got to be the same charge. So over here, we know that this point charge is going to be negative. So we could call this one Q1. We could call this one Q2. So we know Q2 is going to be negative. So that actually answers the question to the what is the sign? The sign is going to be a negative charge. So now we have to figure out the magnitude of it using Coulomb's law. So right here, we don't know how many coulombs. We know it's a repulsive force, so I can draw that in. We know it's a repulsive force. Do we know the distance? We do know the distance, so I'm going to draw that in. We know the distance is equal to 1.07 meters. We know the force that was given is going to be, so force is given to be 1.32. So we know the force, 1.32. Okay, so now we have everything we need to know to find what the Q2 is going to be. All right, so force, I can just plug in those numbers. So 1.32 equals K. I just leave it as K because I know what it is. Q1 is absolute value, so I'll just call it positive, 6.36 times 10 to the negative 6 times Q2 is what we need to find because that's the magnitude, all over R squared, so we're looking at 1.07 squared. Then you solve that for Q. I'm going to save us some time here. You guys know how to do algebra. So Q2 equals, when you solve this one, you're going to get an answer of 2.64 times 10 to the negative 5th coulombs. So that's going to be the charge on Q2. But that's not the full answer because we still need the sign. We know that it's two negatively charged particles, so then therefore our answer needs to be negative. So Q2 would be negative 2.64 times 10 to the negative 5th. Okay. I think you guys have seen these at science fairs, and you probably always wondered how does it work. Well, what it does is it sends a electric signal through your hair, which has the same charge on it. And you guys know that like charges repel one another, so each strand of hair is going to have the same charge. It's going to make it stick up and repels as best as it can from one another. All right, so let's just kind of go back, do a quick summary, and then we'll move on to the next thing here. So Coulomb's law, it's just a way for us to calculate electric force. It's K times Q1 times Q2 over R squared. We take the absolute value of these because we don't want any negative numbers. The sign can be found by reading through the problem carefully, like you guys saw with this one, that it was a repulsive electric force. We had one charge was negative. Let's say you flip the script. Well, if it would have said the attractive electric force, then that problem would have been a positive for the answer. So yeah, that's just summarizing some of the problems you guys will see with Coulomb's law. All right, we're going to switch gears here a little bit. So here's kind of a fun conceptual problem to consider. Let's say we have an electron and a proton are separated. Okay, so picture an electron and a proton. You guys know one's positive, one's negative. Let's say they're separated. Normally they would be attracted to one another. Let's say they are separated, okay? And then they are released simultaneously. The two particles are free to move. So let's just say you go like this and then release those particles. Are they at the midpoint of their initial separation? So let's just say you release them and then boom, they meet right here. Are they, so this is the proton, this is the electron. Are they going to meet closer to the proton, or are they going to meet closer to the electron? I'll let you guys think about that for a second. So you have a proton over here, you have an electron over here, and if you were to release them, where are they going to meet? They meet midpoint, closer to the proton, closer to the electron. Hopefully, you guys answered that they should collide closer to the proton, which makes sense because if you think about it, we learned about protons and electrons in the last video. Proton's so much heavier than an electron. It's like 4,000 times heavier, or 2,000 times heavier than an electron. So if you remember Newton's second law, where you have force equals mass times acceleration, or like they have written right here that the acceleration equals the force divided by the mass. It's going to take a lot more to move the proton than it is the electron. So they should meet closer to the proton. All right, so we're going to switch gears here. Some of you probably have been making some connections as going, hey, wait a second. That Coulomb's law looks awfully familiar. And if you have, it's probably because we just learned about Newton's law of gravity, which is K, they have it written here, kind of funny in our notes, but it's K times, remember, M1, mass of object 1 times mass of object 2, divided by R squared, divided by, well, the K was G. We learned about the universal constant for G. But can you see the similarities in the two formulas? And that's because there is a lot of similarities. They both have, so the Q's, if these are doubled, then this force is doubled. If you double the masses of your planet, then the force is doubled. If you increase the distance by double, then it's by a factor of 4. Same thing if you increase the distance, be by a factor of 4. So they're very, very similar formulas. But let's kind of consider this. in terms of if we're looking at a moon and the Earth, which force is going to have the greater effect on it? Is it the electric force or the gravitational force? Well, to know this, you have to know that the moon and the Earth are basically electrically neutral. Everything kind of cancels you out. So essentially the Earth and the moon, electric force is 0. So then obviously you guys would understand that the gravitational force between the Earth and the moon is going to be way greater. Oop, hold on. But now I'll go back to this. But now what about, like, okay, so the moon and the Earth, those are two big objects. Let's look at at the atomic level. Let's consider a proton and an electron, and let's see kind of what would happen between like the electric force versus the gravitational force. Okay, so if you calculate the gravitational force between a proton and an electron, you get the answer of 3.36 times 10 to the negative 47 newtons. That's based on the mass of the proton, mass of the electron, the distance between them, that sort of thing. And that's what you get, 3.36 times 10 to the negative 47. If you look at like Coulomb's law or the electric force, and if you calculate the electric force between an electron and a proton, you get 8.22 times 10 to the negative 8 newtons. So as you can see, if we compare these two numbers, which force is going to dominate in terms of an atom? And hopefully you guys can see that the electric force is way bigger. It's 2.26 times 10 to the 39th times bigger. So in terms of an atom, the electric force is going to dominate. So that's like what it says there. The electric force rules at the atomic level, whereas gravity plays essentially no role at all. But that's different when you're talking about the Earth and the moon. Which one played the biggest role? Well, it was gravity, and essentially we had 0 electric force. So this brings us up to this fun picture here. This is an artist's depiction of a black hole. A black hole's gravity is so strong that it ends up pulling matter from, let's just say this is a star in orbit around a black hole. It actually pulls the matter from the star, and then it gets sucked down into the black hole where it won't be seen again, and it actually makes the gravity of the black hole even stronger. Alright, so where are we here? So we got a fun calculation to do, and I think I'll leave that one for you guys. So this will be it. Alright, so Niels Bohr is a famous chemist for figuring out the Bohr atomic model. This is kind of how he figured out the speed of an electron. It's kind of a fun calculation. So let's read through this and go through the calculation here. It says, in an effort to better understand the behavior of atomic systems, the Danish physicist Niels Bohr introduced a simple model for the hydrogen atom. In the Bohr model, the electron is imagined to move in a circular orbit around a stationary proton. The force responsible for the electron's circular motion is the electric force of attraction between the electron and the proton. Given that the radius of the electron's orbit is 5.29 times 10 to the negative 11 meters, and its mass is 9.11 times 10 to the negative 31st kilograms, find the electron speed. So we just learned that gravity essentially has no effect on the atom. It's mainly going to be this electric force. So this electric force is going to control the speed of how this is going, the centripetal acceleration, which you just learned about in that last chapter there. So if you set the force of the electric force equal to ma, so mass times acceleration, but in this case, the acceleration, because it's orbiting, is going to be centripetal acceleration. So, and you have the mass of the electrons times the centripetal acceleration equals the force. The force causing it is electric force, so we use Coulomb's law there. If you remember right, or recall, centripetal acceleration can be expanded out to v squared over r, okay? And then times the mass of an electron, and then here's the charge of 2 electrons, that's where e squared comes into play, because that's that times that, so just e squared. R squared times k, and basically solve this for v, and that will tell us the speed of the electron, which is 2.19 times 10 to the 6th power. So just kind of a fun calculation to do. I'm going to actually, just for the interest of time, leave this one up to you guys. So it's a follow-up problem where it says the second Bohr orbit in guided example 19.4 has a radius that is 4 times the radius of the first orbital. What is the speed of that electron? So I encourage you to work this problem out. I'll tell you the only thing that you have to do is change r. So if you're looking right over here, you just have to take r times 4. So if you're going through here, there's your r times 4. So I'll let you guys work through that one. And then you guys will have for today the section questions to complete. So that's it.